So radiant energy emitted per unit time. So here the point already comes, which would explain that the light is given off by the object per unit time. And in the very next line, उसने ये आपको बोला कि this is the same as the total emitted power by the star. So luminosity का जो unit होता है वो watts होता है, which is equals to joules per second. And the nearest object whose luminosity we know and we have calculated accurately is what? Sun. ठीक है? So the luminosity of the star of the sun is given as L dot, which is the value of 3.83 into 10 raised to power 26 watts. We do not need to memorize it, but we need to memorize what luminosity is. Are we clear about this?
Yes.
Then comes the second thing that I explained to you, that I mentioned was the standard candle. Standard candle is an astronomical object of non-luminosity. For example, sun could be considered as a standard candle because we know the exact luminosity of sun. So anything whose luminosity is known as a standard candle. And in order to say, we have two standard candles in our system. The one is Cepheid variable star and type 1a supernovae. Supernovae जो है, we will study, I will give you an overview of that. What we call it, supernovae is basically when a star is moving towards the end of its light, it is a part, it's a process, or it's a phase of the star when it is going towards the end of its life. So supernovae is we could say that is taken out from there. So type 1 is supernovae and Cepheid variable star are the two known standard candles according to which we make the references. Now, important thing comes up that why do we need a standard candle? I mentioned that in the very start of the lecture that these help us to find out the distance of the faraway galaxies. If we want to find out the distance of any galaxy or star, this would help us in order to get those values. What will be the formulas that will use to find that, and how we could do that on living on Earth, that we're going to study in the later section. Clear? Can we go to the next part?
Yes, sir.
So, starting with the standard candle first, which is Cepheid variable star, he said that by measuring the period, astronomer could determine the luminosity of that star, and the star's distance could then be calculated from the observed radiant energy on the earth. जो wavelengths हमारे अर्थ से हमें उसकी luminosity जो receive हो रही होगी per unit time, from that we can calculate the distance of the star. So finding the Cepheid variable star in a galaxy meant that the distance of the galaxy itself could be calculated. वही जो मैंने आपको मीनिंग बताया ना कि what help us, standard candle किस लिए यूज होता है, इसको क्यों हम लोग उसे, cause it help us to find out the distance of the galaxies or stars whatsoever. And supernovae में उन्होंने mention out किया was type 1 supernovae stars implode rapidly towards the end of their life. There is this pattern जो कि study होता है in O levels in the recent studies that whenever star is towards its death, end of its life cycle, there comes 3 to 4 phases until it ends. और उस टाइम पे भी जो luminosity जो है, जो light वो emit करेगा, जो spread out करेगा, from that we can find out the distance of that star. Okay, so first let's say what supernovae is. There is this term used as main sequence. Ever heard of main sequence?
नो, नहीं।
आपको इतना तो पता है स्टार्स के पास फ्यूल होता है, और वो फ्यूल क्या होता है हमारे पास? हाइड्रोजन।
हाइड्रोजन।
ठीक है। when 12% of that fuel is used, stars in जो star into enters into a phase which is known as main sequence. After main sequence we see how much solar mass is left to the star. सोलर मास कहते हैं मास ऑफ द सन, comparison to the sun. So let me take you to the whiteboard. So main sequence के बाद if the mass, the writing is very bad, main sequence के बाद if the mass is greater than 8 solar masses, obviously जो fuel left है उसका mass greater than 8 solar masses है, the star enters into a super red giant, then supernova, and in supernova के बाद if the mass of the planet of the or the fuel left is less than or equal to 3 solar masses, so वो बन जाता है न्यूट्रॉन स्टार, and if it's greater than 3 solar masses we get black hole. ओके, सो सुपरनोवा वहां से आया कि when it's वो उसने लिखा है ना बुक में वो टर्म, लेट मी टेक यू बैक टू दैट, उन्होंने सुपरनोवा का टर्म ये देखो क्या लिखा हुआ है, स्टार implodes rapidly towards the end of their life, cause after that वो क्या होगा, ब्लास्ट ऑफ होगा, ठीक है, इनटू ईदर न्यूट्रॉन स्टार और ब्लैक होल। ब्लैक होल से तो आप फेमिलियर हो गई, ब्लैक होल की टर्म आपने सुनी हुई है, ठीक है। सो टाइप वन इज सुपरनोवा स्टार implodes rapidly towards the end of their lives and scatter matter and energy into the space, ठीक है। ऑब्वियसली जब स्टार जो है इट विल जो है एक्सप्लोजन, जो बिग बैंग थ्योरी जिसको वो जस्टिफाई करते हैं ना, सो ये वो है कि व्हेन इट एक्सप्लोड्स तो वो मैटर और एनर्जी जो है वो इनटू स्पेस, वो ग्रेविटी वेव्स के बारे में सुना है ना आपने, ग्रेविटी वेव्स डिस्कवर हुई थी। ओके, नहीं सुना हुआ, एनी हाउ लेट्स जस्ट स्टिक टू दैट पॉइंट कि व्हेनेवर समथिंग व्हेन द स्टार इज टुवर्ड्स एंड ऑफ इट, वो फाइनली इट बर्स्ट इनटू मैटर एंड एनर्जी जो स्पेस में थ्रू आउट जो है वो स्प्रेड आउट हुआ होता है। अब वही वाला पॉइंट जो मैंने अभी आपको बताया कि this employee even can be brighter than the galaxy itself, the luminosity of that star at that time of the moment is always the same. From this, astronomers can estimate the star's distance from the earth. So standard candle और luminosity का मीनिंग क्लियर हुआ? Okay, moving on to the next part. Okay, now the next part that we're going to study today is luminosity and radiant flux intensity. Radiant flux intensity has the formula is given as F, which is equals to luminosity, that is power. Its luminosity is basically power, total power emitted by the star, divided by 4 pi d square. As we have just studied in the previous part, the luminosity is a constant factor for a given star. Okay? So, if L over 4 pi is a constant, then F has an inverse relationship with the d square. Radiant flux intensity has an inverse relationship with the scale of the distance. Inverse scale law follow up kara. Clear?
Yeah.
Before getting into that, let's discuss what is the meaning of light year. Light year is defined as a distance traveled by light in 1 year. Distance traveled by light in 1 year. Why do we use this unit of distance? And light year को LY से denote करते हैं and it's given in meters because it's a distance unit. Why is that? उसने यहाँ से क्या हुआ है कि distances जब हम measure करते हैं for galaxies and anything, वो extremely large होते हैं. So in order to deal with that, we use the unit 1 light year, which is उन्होंने given किया हुआ है. Distance का formula क्या होता है बच्चों? What is the formula of distance? Speed into time.
Speed
If we
time.
are discussing about speed of light, that would be 3 into 10 raised to power 8. And time हमने क्या discuss किया है? 1 year. So 1 year has 365 days into 24 into 3600. That would be given 9.5 into 10 raised to power 15. So Proxima Centauri is the nearest star after sun, which is approximately 4 into 10 raised to power 16 meters away from us. So if we mention that in terms of light year, this would be 4.2 light years away from us. Okay. In the next part, we're going to study that how luminosity is dependent on distance and temperature. ओके टेम्परेचर तो हम डिस्कस करेंगे ब्लैक बॉडी रेडिएशन की बेसिस के ऊपर और उसी में हम लोग डिस्कस करेंगे वेन्स लॉ वेन्स कांस्टेंट सॉरी एंड स्टीफन बोल्ट्जमैन कांस्टेंट दैट विल बी फॉर टुमारोज लेक्चर फॉर नाउ वी आर गोइंग टू डिस्कस दिस थिंग आर यू क्लियर अबाउट लाइट ईयर
जी जी
okay going on to the next part here उसने कहा from table we could see that if the distance and luminosity दोनों आपस में उसने कहा है कि normally जो है जो brightness है हमारे पास it could depend on the either distance and luminosity generally but हम लोग इन दोनों को आपस में अगर हमें relate करना है कि brightness जो है is dependent on luminosity or not तो हमें इन two factors को अपने mind में रखना होगा. If we want to say the brightness of the star is related to luminosity, the power of the star is uniformly radiated throughout the space. जो constancy वाली luminosity की बात की थी ना मैंने वो वाली, and there is a negligible absorption of this radiate power between the star and the earth. Then we can relate the luminosity with the brightness of the star. अगर हम इस ग्राफ पे वापस आए साइंस टेबल पे वापस आए we could see that इसका डिस्टेंस कितना है 310 और इसकी ल्यूमिनोसिटी कितनी है 1100 whereas इसका डिस्टेंस कितना है 4.4 एंड इसकी ल्यूमिनोसिटी कितनी है 1.5 बट ये जो है इट अपीयर्स मोर ब्राइटर टू अस देन Arcturus which is 37 light years away from us and its luminosity is 170 so अगर हमें brightness को relate करना है with the luminosity तो हमें इन factors को अपने mind में रखना है and here we have the radiant power, flux intensity formula radiant flux intensity equals to power of the star over surface area of the sphere 1 over 4 pi d square so d square यहाँ पे star of luminosity L distance and ये जो पाई डी स्क्वायर जो है वो यहां से उसने फॉर्मूला जो है 4 पाई डी स्क्वायर ओके इसकी बल्कि एक अच्छी रिलेशन भी जो है ना लेट मी शो यू फ्रॉम दिस बुक यहाँ पे उसने डिस्कस किया दैट एरिया ऑफ अ स्फीयर किसके इक्वल होता है पाई आर स्क्वायर के इक्वल होता है एंड पाई आर स्क्वायर इक्वल्स टू अगर आप उसको पुट करें तो पाई आर इज इक्वल टू डी बाई टू पाई कैंसिल आउट हो जाएगा डी वन ओवर डी टू सो एरियाज are directly proportional to the distances. So जितना ज्यादा डिस्टेंस होगा उसकी लाइट उतनी ही ज्यादा क्या होगी स्प्रेड आउट होगी जो कि इस पॉइंट को वैलिडेट करती है जो उसने यहाँ पे लिखा हुआ है ये द पावर ऑफ द स्टार इज यूनिफॉर्मली रेडिएटेड थ्रू स्पेस सो देखो अगर इसमें हमने डिस्टेंस को बढ़ाया है d1 to d2 we could see कि it's more spreaded out okay it would appear more brighter. सो ल्यूमिनोसिटी को अगर हमने ब्राइटनेस के साथ कंपेयर करना है सो हमें इन दो पॉइंट्स को अपने माइंड में रखना पड़ेगा सो रेडिएंट फ्लक्स एंड डेंसिटी इज गिवन एज पावर ऑफ स्टार व्हिच इज L over surface area of the sphere which is 4 pi d square and the unit of radiant flux density is watts per meter square And for a given star, luminosity is constant. उसने again वही बात की है. So according to the equation, the radiant flux and जो बेन फर्स्ट स्केला जो मैंने अभी आपको ऊपर जो है वो explain किया भी था. So doubling the distance from the center of the star will decrease f by a factor of 4 and tripling would be by 9. So practically उसने आपको यहाँ पे show किया हुआ. So astronomers on the Earth can determine the radiant flux intensity of a distant star using this formula, and this could be rearranged to remind the distance of a star of known luminosity. For example, a standard candle suggests Cepheid Vivisar, and उसने आगे that Hubble's was the scientist who found out that when it comes to the space physics, there is a direct relationship between speed and the distance. That means the further apart a particular star or planet is, the more speed it will have. At the same time, I would like to add a point that when it comes to the planetary motion, the when the planet is closer to some bigger planet, obviously we have studied that the gravitational pull is the main reason of the centripetal motion of that object. Okay, and is always acting towards the center of that object. So whenever the planet is closer, its speed is greater, which means its kinetic energy is bigger. And when it goes further away, its GPE increases. So when it's coming closer to the planet, to another planet around which it's rotating, so the gravitational pull will be greater and this it will accelerate the planet. And due to that acceleration, that planet will bypass it and will go to the further point and then will come back and this process will go on. Just consider that you have attached a ball with a spring or any elastic object. When we'll throw it further away, when it reach to the maximum point, will it come back or not?
Well,
It will come back to you again. Okay?
आएगा.
And it will not stay with you, but it will bypass you. And this process, if the force is continuous, if I keep on juggling it back and forth, this process will go on. So consider the planetary motion the same way that the gravitation pull is like an elastic string in between the planet, and it's pulling in and out. And when it's getting closer to the planet, to the bigger planet, like the sun, so the acceleration, it will be accelerated, so its speed would be greater and kinetic energy in return would be greater. And it will be at when it will be at its furthest points, its GPE would be greater because GPE depend on h. So when h is greater, GPE would be greater. So Hubble's law, taking help from Doppler's effect, came up with the formula, and he said that speed and distance directly proportional. The further away the planet would be, greater would be its speed. Now it somehow contradicts with the planetary motion, but he took help from the Doppler's effect. And Doppler's, what did the Doppler said? That there is a change in frequency of the object of the source if there is a relative motion between the source and the observer, right? We have the formulas of the Doppler's effect. We have the form now getting on to the Hubble's law. Hubble's law is h is equals to v over d. Here v is the orbital speed of the object and d is the distance of the object from the sun. If we stay in in our planetary system, that would be the distance from the sun. Hubble's is a constant and its value we'll discuss it in a bit. This is Hubble's constant. So h into d equals to v naught, and if I'm considering a constant, then v would be equals to d factor. So Hubble's law also help us to find out the age of the universe, and that again we'll get it from the formulas. I'll just show it to you. Let me share my screen. Hold on. So Hubble's uses data of the speed of the planet versus distance of the planet, and he drew a scatter graph out of it, and he found out that there's a relationship between V and D, which he further on explained as that as there is the as the distance increases, distance of the planet increases, the speed of the planet also increases. We already have discussed that. Here you could see it's mentioned in light years. So whenever we're discussing about when we are studying astronomy or cosmology, we go on with the unit of light year because that's a very distance the relation we do. So the Hubble's constant h naught equals to v over d, where v is the orbital speed and d is the distance of the galaxy from the Earth, or whatever we're discussing. So by putting in the data, they found that the Hubble's law is equals to 2.2 into 10 raised to power minus 18 per second. Using this constant, they found out the age of the universe. Now, we need to focus here. We know that h equals to v over d, right? And if I write it as h, so this would become d over v, which is the formula for time, because v is equals to d over t and time equals to d over v. So by putting the value of Hubble's constant into this, we found out the age of the universe, which is 14.14 into 10 raised to power 9 years. So that's all we need to know about Hubble's law. Hubble's law depends on Doppler's effect. Doppler's is the effect which explains to us that there is whenever there is a relative motion between the source and the object, there would be the change in frequency. And using the Doppler's effect, they explained the redshift, the absorption spectrum, and the emission spectrum. Do you guys remember from the hydrogen when we discussed the hydrogen spectroscopy? The from the cold gases and the hot gases.
Yeah.
Then when a gas was passed through when the light was passed through a cold hydrogen gas, there were certain wavelengths which was absorbed by the gas, which was known as absorption spectrum, and they from that we came up with the idea of redshift as well. So when the light coming from the distance planet or faraway planets or stars, you could say, it was observed on Earth using the standard candle results and everything that we discussed in the previous lecture, that the wavelength was shifted towards red and certain wavelengths were shifted towards blue. So the wavelengths which were observed by a star on Earth and was shifted towards red, that explained us that that system is going away from us, and the one that showed the blue wavelength, blue shift, that explained us that that particular planetary system or system, planetary system is the wrong word to use, that system is coming closer to us. So ये जो phenomena हैं, these are used in everyday routine as well by the, if we want to check the sonar system. Do you guys familiarize with the sonar system? That is used by the bats and the planes, by the airports, and by the submarines as well to check whether if there is anything closer or not. If there is the the observed wavelength is smaller, that means it's shifted towards blue, that something is closer to us. If the wavelength is shifted towards red, that means that object is further away from us. Are you getting that point?
Yeah.
So when the Hubble's law was found out and the shifts were checked, and it came to our knowledge that universe is continuously expanding and everything is going away from us. Even our solar system is expanding day by day, and by expansion we could come up with an idea that we have a balloon with air in it, and we are if we increase the volume of air into the balloon, it will expand, so everything is going away from each other. So that's what the Hubble's law and the age of the universe and the redshift जो है helped us to understand that everything is going away from us, everything is expanding, the universe is continuously expanding. And you might have uh, studied or seen somewhere that the universe is continuously moving away. Even our solar system is not stationary. Do you guys know this?
हाँ, कुरान में भी लिखा हुआ है.
Our solar system is not stationary. It's going into a spiral motion, continuously going forward, expanding. So going on to the Let me clear that out and let me show you that part. The Hubble's law portion. I'll get back to the standard candle part. Here they have found out the relationship using Doppler's factor. Here you could see they have discussed that the speed and the distance is proportional to each other. When we remove the proportionality sign, we get the H, which is the Hubble's constant. Here the absorption spectrum is discussed, and the redshift. Let me read that part to you. The observed wavelength of sound was longer for a receding source and shorter for an approaching source. So the receding source longer, which is going further away, and approaching source shorter wavelength, this would show the blue shift. The same happens with electromagnetic waves. The observed wavelength of all spectral lines from distant galaxies are longer than the one observed in the laboratory. This is known as redshift. The redshifts of spectral line from distant galaxy must imply that all galaxies are receding from us. This is what American astronomer discovered in 1917, and the American Edwin Hubble observed, combined his own observation to create Hubble's law. And this is the Hubble's law. And here might have the value is 2.4 into 10⁻18. This is the scatter graph that I showed you before. Speed versus light year. Doppler shift. Are you guys familiar with this equation?
No.
V is equals to F lambda.
Wave equation.
Oh, yeah.
So here they have mentioned that it's worth pointing out that the term redshift does not employ spectral lines becoming red. Again, that's a very important line. It does not mean that the lines are red, but it is shifted towards the red wavelength. The fractional increase in the wavelength depends on the recession speed of the galaxy. For non-relativistic galaxies, those moving at speed far less than the speed of light in vacuum, we can use the relationship delta lambda. Delta obviously change in wavelength. Lambda is the original wavelength. Delta F is the change in frequency over original frequency equals to speed of that object versus speed of light. So using that, we can get this. This will help us to find out the redshift. So there they have put a value. Astronomers in cosmology often assign a value of the redshift. For example, a galaxy shows redshift 7% means that it's equals to 0.007. That's a basic percentage. Let's see if this example could help us out. And the Laportian emission spectral line is lowered at a wavelength of 6. They have given us the wavelength. The spectral lines, the spectrum of distant has a wavelength of 663. So इसमें original wavelength कौन सी होगी? जो laboratory वाली and observed wavelength 663. So calculate the speed of the galaxy. Change in wavelength find out किया. Change in wavelength came out to be 6.7. Original wavelength was 656. Putting it in the value, we found out the speed of the which was 3 into 10 raised to power 6 meters per second. Evidence of the Big Bang, the balloon thing I was telling you about that. Consider that there's a balloon with all the our Milky Way. It's continuously expanding with time. You'll read everything here in the same way. And that was the age of the universe that I showed you before by putting in the values of the everything. So the black body radiation, the I discussed about the black body. How do you define a black body?
Which absorbs all the
A
wavelengths
black
and
body is an
observes
ideal
everything.
observer. So scientists performed certain experiment and they found out that the maximum wavelength emitted by the body is directly proportional to the temperature. Greater the temperature, greater the. But there is a maximum wavelength at a particular temperature above at a particular intensity. For a particular temperature, a maximum wavelength which is proportional. So lambda maximum is equals to constant so sorry, they found out that the product of maximum wavelength for a particular temperature is equals to constant, and that constant is the Wien's constant, Wien's displacement law, and its value is given as 2.9 into 10 raised to power minus 3 meter Kelvin. So this maximum temperature, ये मैंने आपको explain कर दिया कि at a given temperature the emitted energy has a maximum value of certain wavelength and the product is there. And further on they found out that they drew a graph, and the graph is given in the further, that as the intensity increases there is a maximum wavelength upon a temperature the maximum intensity, maximum wavelength at a particular temperature. And this maximum wavelength increases as the temperature increases. Let me take you to that point so that I don't have to draw this kind of a diagram here. For intensity, you could see that as the temperature increases, the value of lambda versus intensity also increases, right? So the product of maximum wavelength and temperature, matlab the temperature at which it had that maximum wavelength is equals to Wien's displacement law. Also, this area under the graph also help us that the total energy radiated per second per square meter over all wavelengths at a particular temperature. And it was also found out that the area is directly proportional to the fourth power of temperature, because we already said that the area under the graph is the energy radiated per second, so we could also write it as E proportional to T power 4. And here we got the constant sigma T4. The sigma is Stefan-Boltzmann constant. Boltzmann constant, and its value is given as 5.67 into 10 raised to power minus 8 watts per meter square into Kelvin power 4. So that's Stefan Boltzmann constant and law and Wien's displacement law so far. So the higher the temperature of the body, the shorter the wavelength at the peak intensity, as I showed you here. Peak intensity, shorter wavelength at greater temperature. The greater the intensity, the electromagnetic radiation at each wavelength. This is the formula. Wien's displacement law, and the value is given as 2.9 into 10 raised to power minus 3 meter into Kelvin, because we have wavelength, meter, and temperature. The surface temperature of the sun is 5800 Kelvin. This gives a wavelength value of 5 into 10 raised to power 7 meters or 5 nanometer. Light of this wavelength appears yellow. So somehow this law was also justified when we studied the result using the sun data. And then Stephen Boltzmann law, it explains that the luminosity of a star depends on two factors, its surface temperature and its radius. So L equals to 4 pi sigma r square into T4. Do you remember ये formula हमने पहले भी किया हुआ? L over 4 pi r square किसकी इक्वल होता है? Radiation flux density. Radiant flux density. Right?
Yes.
So using immense displacement law and Stephen Boltzmann law to determine stellar radii, because दोनों के अंदर हमारे पास radii आ रहा है, इसके अंदर हमारे पास r की वैल्यू आ रही है, उसमें हमारे पास wavelength आ रहा है. So use it to determine the temperature of the star. This will involve determining the wavelength at maximum intensity for the star, which standard candle का portion to discuss किया था, and then using a reference star such as sun to determine its temperature. And Stephen Boltzmann law to determine the radius of the star. The luminosity of the star can be determined by measuring the radiant flux density, as I just discussed it. Because L over 4 pi r square किसको शो करता है? रेडियंट फ्लक्स डेंसिटी को शो करता है. उसको पुट करेंगे वेन्स डिस्प्लेसमेंट लॉ से, हम उसका यूनिट निकालेंगे एंड उससे हम लोग आर की वैल्यू कैलकुलेट कर सकते हैं. यानी इन दोनों को साइड बाय साइड यूज कर सकते हैं हम लोग. ओके. बाकी जो स्टैंडर्ड कैंडल का पोर्शन था वो हम लोगों ने ऑलरेडी डिस्कस कर लिया. तो स्टैंडर्ड कैंडल क्या होती है? whose luminosity is known. Irradiant flux density का फॉर्मूला भी आ गया. स्टैंडर्ड कैंडल हमारे पास क्या होती है? जिसकी ल्यूमिनोसिटी नोन होती है. ल्यूमिनोसिटी क्या होती है? रेडिएंट एनर्जी पर यूनिट टाइम. एंड एनर्जी पर यूनिट टाइम किसको शो करता है अली?
Power.
पावर को. यस.
Power.
एंड इफ वी आर कंसिडरिंग सन तो उसके लिए हम ये वाला सिंबल यूज करते हैं. That's the end of this chapter, the light year that I explained to you earlier. Radiant flux density L over surface area, distance of the galaxies, and yeah, that was discussed in the previous lesson. Let